Hey then, the thing has been hit. The thing says we're on. All righty, everybody. You guys, what's going on? Memes here. Yes, I am wearing a traditional yellow shirt today. Again, no sunglasses because I kind of actually want to be able to see what the heck I'm talking about. Okay, so what are we talking about for today? So, as we let folks roll on in and join into the chat again, this is going to be the sixth episode. Yes, yes, I'm actually being consistent with something for once of my monastery life. And the whole point of this chat is to just talk about sciencey stuff and things, maybe be a bit of an escape for some people for even a short period of time. Again, we go basically an hour long. We discuss different stuff and things that people bring up, or I just happen to be literally working on earlier and be like, that's an interesting little coinky dink. So for anybody that actually looked at the thumbnail and that was not brought against here by their will, by the algorithm, feel free to do all the algorithmy things that you want. I ain't the boss of you. But for those that looked at the algorithm, excuse me, the thumbnail, yeah, yeah, algo's on the brain. Ain't that the story of modern life? Um, Basically, at one point, Thad, we had brought up something about looking at the different dimensions of reality, yada yada, and you find out you got five-dimensional ingredients: time, space, charge, mass, and temperature. And from that, you can make up all the different constants of nature. And again, you got to apply some mass. Occasionally, there's a pi, there's a two pi. Uh, ooh, Rick, Rick, I'm gonna say something. It's again, you can take this however you like. I think you should come to me to the Wolfram Summer School this upcoming year. Personal opinion. I think it'll be a lot of fun, and I think interesting things would happen. Just a personal opinion there, because I totally didn't do it last year. I did not learn enough code. I applied far too late, and I was making up excuses in my head. I am going this year. Why? Because I got it. Because at some point we're going to need to actually get some ideas out there and actually get some funding. We don't need an enormous amount of funding, just enough funding to, like, I don't know, like have a place and some food and standard utilities, all that jazz. So, okay, what are we talking about today? Today, uh, we had a discussion. It's like, all right, because I know even Rick here in the chat is stressed. Looking at things inversely can often reveal very interesting things. So let's look at maybe the Planck mass. Okay, so here's what we'll do. I'll open up another tab. We have to build up to the suspense about what the heck we're talking about, even though I kind of went ahead with the thumbnail. But all right, so let's go over to this window over here. All right. Don't look. I need to swap the window. Hold on. Okay, I duplicated the tab. I'm sorry. Spoilers. Spoilers. I know. All right, so we got the Planck mass. What the heck is the Planck mass? Okay, it's the theoretical, I would claim, maximum unit mass for particle-ish things. Okay. Yeah, yes, I'm literally wiggling my fingers there like some sort of magic. Why? I don't know exactly what it is. Apparently, if you crunch down something to the Planck mass and it's scrunched down within like two Planck lengths, you essentially get your Schwarzschild metric, yada yada, black hole, mass hole, whatever the heck those things are. Okay. So basically, in kilograms, some folks may say grams is a better measure. There are arguments for that, but in kilograms, we're basically at 10 to the negative 8. Okay. So what would happen if we looked at this upside down? And again, we're taking some shots in the dark here about what might be going. Oh, we get like 10 to the 7 reciprocal kilograms. All right, let's be very lazy. What are we gonna do? Let's let's literally just tear out the reciprocal. I know, a savage move. All right, so we got about the mass of the Titanic or a standard cargo ship. Okay, let's make everyone feel better about themselves and get to this in a real way. Rather than doing that, let's what do we get? Kilograms squared. Why? So we'll get a dimension of mass. Okay, I say this is a mass hole. Okay, so we get the same thing. Now, that in itself, I'm like, all right, that's kind of cool. So I started playing with the masses, and coincidentally, even for our conjectured mass of the electron there, basically, we do this little trick. We have Let me go back. So we're going to do the Planck mass to the fourth. And we divide by kilograms raised to the third. What does that get us? Uh, it's about 10 to the negative 31 kilograms. All right, so we're kind of close to the electron mass. And then if anyone wants to do a practical joke on somebody, you could always do 2 figure A naught volume. You multiply it by that, and oh, what's this? Oh, 9.11 times 10 to the negative 31 kilograms. All right, that looks especially close to the electron mass, but there would need to be a correction term. That's where the second component comes in. But we're not here to talk about electrons or conjecturing their mass or anything like that, even though that's what I just did. All right, let's go back to something simpler. Okay, so what happens if we were to do something like this, except we did this? I'm going to type some magic words here. By magic words, I'm just going to kilograms to the fifth. So we extract out a dimensional thing and divide it by the Planck mass raised to the fourth. Why the heck am I doing this all, you might ask? It's all right. We're getting to a point, I swear. We get 4.4 times 10 to the 30 kilograms. Again, that doesn't mean anything to me. That's a lot of mass. I think it's greater than the mass of the Earth. It's like 10 to the 26 kilograms. Something like that. Oh, 2.241 solar masses. All right. So a little over twice the mass of our sun. All right. That's at least a little interesting. I can try to somewhat imagine that, even though that's so much more ginormous than our meterish existence and dozens of kilograms, even hundreds of kilograms masses. Okay. And then here's where it starts getting really interesting. Comparisons as mass. Okay. Okay, so zero point 0.1 to 1.1, a massive B-type main sequence stars, all right? So, stars. So 2 to 16 masses. And then, oh, 0.9 to 1.3. That seems to be approximately the mass of A-type main sequence stars. And within our standard convention, apparently within, I'm going to say astronomy here. I'm sure a cosmologist will get very angry. I'm sorry, Professor Keating. But we're entering the stellar mass scale here. And then for the sky, it looks like it's going to be a color bluish, temperature class, yada, yada. All right, lifetime about 1.3. All right. So coincidentally, if we're using the same magnitude of the Planck mass, just relating it to what we're helping to define it by the kilogram. And yes, I know we're doing H bar and we're doing all these other jazz and everything to define it. That's why we only have like 5 significant digits to the Planck mass within colloquial parlance and literature. Again, we claim to have logarithmic closed forms. Maybe they're right, maybe they're wrong, but at least that gives us a method to utilize as a form of a scalar, if you would. As long as we're not moving, as long as there's no vector or anything, we can use it as a scalar. As soon as we do that, then it breaks. I know technicalities. But we want to be precise as best we can. No? Yeah. Oh, again. Good to see you, my friend. I hope you're doing a little bit better. I see stuff pop up, but everyone's always busy and there's always jazz going on. But good to see you, my friend. Um, okay. So wait a second. Why is it if we're just taking the mass that we're happen to be using, just generally in a slightly different form, for calculating the elementary unit, the elementary unit of mass that we are actually plugging in to basically derive all the other mass functions and other things within our model here of the monastery. Okay. So I'm just like, all right, let's just do the naive thing. Let's just flip it upside down. We still need a dimension of mass. How can we justify this? Oh, okay. Well, we're using 5 dimensions of measure. Okay. And we happen to get out something that seems to be of the magnitude of, it looks like most of the stars where we live, or at least that we've observed. And again, it's of the magnitude. You could change it a little bit this, or you could do something fancy like this, and I'm gonna do the reduced Planck's mass. What's the difference? 2 times the square root of 2 pi. And you get 2.8 times 10 to the 33 kilograms. What is that? That's 1,400 solar masses. It's about 12 times the mass of the primary star, Eta Carina. So that's about 120 solar masses there. And coincidentally, what is it? If we go down to, yeah, it's pretty big and pretty sure that would go into a black hole. We're going to get to a second part because we may have found a lot of dark matter. Now, it's a very interesting thing. We'll get into it in just a moment. But okay. So he asked, I'm like, all right, what else could I do with this? What if we went up again? Just for fun. And again, this is just just speculation here. We're just a little bit of numerology, and again, we have really no zero significant digits here. So kind of like the neutrinos, if we can get the mass of no, let's just do that for a second. Let's go over to this guy. All right. So and again, just an arbitrary claim, just an arbitrary claim. I think we can do what was it? Uh, 8 pi. uh, 8 pi times, how do we have it? We had, okay. So we had Planck mass to the fifth divided by kilograms to the fourth. Boom, boom. And this gives us, so we're getting, I feel like this is off. I feel like it should be 10 to the negative 39. Let me just take out the 8 pi. Yes, live science. We're doing it live, folks. I know, I know. Uh, Hold on. I'm just very dumb here. Point 0.6. No, I think that's our answer. Yeah, that looks right. So was it 0.68 electron volts? Ah, yes. Why? Because our neutrino masses are should be a neutrino mass. I know. It's not like I've done this several times. Let's go to news because we've had news about that. Let's see, science news. I think this is the article we did before. Yes, yes. I want you to sign in. They need to get you for money somehow or another. Good old capitalism. I won't comment more on that because we're already angering enough folks on the internet. As long as they don't come across this, we'll be all right. Hold on. We had I think it was zero point 0.6 or 0.6. Yes. We just Oh, wow. Is it really trying to charge me now? Wow. I've gone too many times. Hold on. Let's just, me. Oh, God. So many clicks. So many clicks to just try to get information. Wow. I do not know. No, I'm not signing up. Okay. But, okay. So let's just go to the board. We'll just go to the board because we literally did this the other day. Okay. So, okay. I need to at least bring one article. Scholar. Blah, 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 blah. Here we go. I think this was from uh, okay, we're kind of in the same magnitude over here. This is from a few years back, and I think they've directed this down. So at least I'm not just throwing complete hot speculation out there. Sensitivity of about zero point 0.7 electron volts, blah blah blah, zero point 0.8. Okay, so that's about a magnitude off. Uh, where is that? Uh, oh, this one of the papers I had. Let's see. Okay, as yeah, all right. They're showing smaller things. All right. So at least it can be no lower than 0.06 electron volt. Again, we have zero significant digits of confidence. We're basically shooting around the magnitude. Okay, so we'll go, oh, hey, nerdy. And we're just going back in the board. We're just going to do a real quick refresher from the other day. So basically, the some of the mass of the neutrinos. Okay, so we're gonna do all right, so summation, blah blah blah. Crazy thingy here of the mass of the uh neutrinos. Okay. So it's got to be greater than 0.06 electron volts. And then the other parameter that they had from the other day, according to that article that wants me to sign up, how dare they try to pay their people and stuff. I know, I know. Personally, I think I would like to see more funding to useful science and stuff, but that's a personal opinion. All right, 0.07 7 electron volts. Okay, so what's a little thingy that we have over there? Let's go back. Boom. We pop over here again. Let's go back to our window. All right, we got that. So we go to. Oh, all right. So what we got here? All right, we got 0.06885. All right, so I got 0.068. Can't remember. It's 885. Okay. 0.06885 would be the equivalent in EV divided by C squared. All right. So that's technically what these are too. All right. So we got, all right. So apparently it looks, I should actually embiggen it so people can see. All right. So it at least looks like, according to these, basically, okay, if we assume that this was correct and we are within a magnitude, and we have a very narrow range for the sum of the masses of all three flavors of neutrinos, okay, is 0.06885 greater than zero point 0.6? Yes. Okay. Is 0.06885 less than 0.07? Yes. Does that mean it's right? No. No, it doesn't. It doesn't mean it's right. It's at least a method to try to simplify to get to a magnitude. And then you got to try to calculate all the flavors, and you're assuming that, all right, the tau is probably the most, so that you might have some other inverted hierarchy. Maybe there's like a zero mass neutrino or anything. It's like, and again, that's the general thought process of what might be going on. Personally, I really should just use the Cody equation and be like, all right, if this is the sum of all these, and the Cody equivalence is going to hold, because that apparently seems to hold for the Cody equation is basically if you take the sum of the masses of our lepton friends, so the electron, the muon, and the tau, and you divide them by like the sum of the square roots, it ends up equaling about like 2/3 to like 6 significant digits. So we'll just bring that up right now. So uh Code equation. All right, let's share it with friends. Okay. All right, the Code formula. The Code formula is this thingy here. Okay. So mass of the electron plus the mass of the muon plus the mass of the tau. You divide that whole thing as, oh, I got it wrong. It was you sum the square root of the mass of the electron to the square root of the mass of the muon to the square root of the mass of the tau, and then you square the whole thing, and there appears to be this relation. So 0.6666661 error bars of 7. So it's approximately 2/3, and then we got, excuse me, 5 significant digits of sixes. Um, I mean, do we really have a huge amount of confidence for the mass of the tau beyond that? I mean, we got, I think, the muon mass to about 12 significant digits or so. Get the mass of the electron to about 12 significant digits or so. Um, so yeah, apparently we could probably break it up and try to partition it like that. Uh, I did another calculation and it was a little bit off and everything, and didn't get back to the magnitude. But okay, so now since we're done with that, we can get back to the other thingy that we were talking about here. Okay, so what would happen if, okay, again, we've got, oh, I did the window, not the, excuse me, I did The tab, not the window. Apologies there. I know. Professional YouTubers. Yes. All right. All right. So I got this expression here. So what if we went up one more order of magnitude? Like we were just showing there. Okay. So we've got kilograms to the sixth by the black mass to the fifth. Why? Because we can. Not saying there's anything like spectacular or anything, but gives us 2 times 10 to the 38 kilograms. So a ginormous amount of mass. Okay. So we've got the inferred mass, a fraction, about 1/1000th the inferred mass of the largest known black hole. So basically, we got the mass of 2 times the mass of a typical globular cluster, so a whole bunch of stars. All right, so we got about 10 to the 7, 5.6 times 10 to the 7 of the stellar mass scale. Why? Because we just throw in another Planck mass. So that's if it's going to give us of that order of magnitude, it's going to go up since we're already at basically the stellar mass scale. Okay, what happens if we do it again? Let's say kilograms to the seventh, Planck mass to the sixth. Go. I mean, I just did one over this before, so it kind of made a slightly different sense, but this is a more correct way or direct way to get it. All right. Oh, 9.4 times 10 to the 45 kilograms. That is a lot of kilos, my friends. All right. So we got about 0.5 times the mass of the local supercluster. That's a lot. Okay, 4,200 Milky Ways. Milky Ways. I always preferred them to Snickers. That is again personal opinion. All right, that's like 50,000 times the mass of the largest known black hole. Okay, I'm slightly confusing myself. Let's unconfuzzle myself. Let's go back because this is an interesting thing you can do. What happens if you use the reduced Planck's constant? Why is it even here? I mean, we have excuse me, the reduced Planck mass. I'm confusing that with h bar. We occasionally use that for simplicity. One is a 2 pi factor. The other is 2 times the square root of 2 pi. Why might that be? Those are fantastic questions. Maybe someone out there has a really good answer for it. We'll see. But basically, if we use that, we come down to a lot of stellar measurements and about 3 times the mass of the inferred largest known black hole. Okay. So we're at least within stellar parameters there. But does kind of scare me is if we're going to claim where we live, our colloquial universe, again, I say that in quotes because we're conjecturing there's a finite size, ginormous, about 8 orders of magnitude larger than the current observable universe. Again, we're going to need different measurements and stuff like that. Experimental verification, or at least see, maybe we can rule out some things. The terrifying thing is if we assume that I think this. No, we need to go forward. Oh, but yeah, but basically, if we do that to the seventh and the sixth, that becomes a terrifying mass scale. Because at that point, it's like, wait a second. What happens if there was a black hole 50,000 times the largest black hole that we seem to have observed? That would be terrifying. That might mean that there will be monsters out there that we haven't even comprehended yet, or at least maybe we could try to comprehend. Now, I have no idea if any of that is true, um, but I think our initial look at these things along the lines of maybe something like this that happens to. How do we have that? We're using reduce. Just use the Planck mass for that. All right, we're basically getting a lot of our main sequence out of this right here, and we're basically pretty close to the stellar mass scale as we have defined it and everything. So I just think that's just kind of a cool thing that you having to get this out when you're just relating very simple things. And again, I'm not saying that this is the reason why there are stars, even though I have is this why there are stars question mark in our little quotations down there. Uh, it's a question. It's a question. It seems to be an interesting coincidence. And Well, if we already have these things and we already have tools that can quickly do a quick analysis at a first level approximation, and we can see some interesting things, I'm just saying if we went back 100 years and we happen to have all the data that was available at the time compiled very neatly, easy to access, with modern computing power and stuff. I don't know. With some of our friends be sitting there doing going down a Wolfram hole or something. I don't know. Some folks prefer maybe pen and paper. That's totally fine. You can do what you want. I ain't that smart. I need a little prompting, if you would, to get me going, to be like, oh, I type in random things. Is there anything interesting about this? Again, 4.457 times 10 to the 30 kilograms. That doesn't mean a thing to me. Where's my reference point as a human being, as an observer, whatever that might be? That's like, oh, a little over two suns worth of mass. All right, sun is ginormous. Make it a little over twice as ginormous. All right, I can at least relatively conceptualize. All right, that's bigger than what we got over there. Sun would be larger. Okay, and it happens to correspond with some stellar mass scales. That is also cool, I would claim. Oh, hey, Kali. Uh, oh, that's an interesting thing. Kali's saying that we need to be measuring mass and neutrons or Planck particles, something inherently meaningful. Oh, welcome, K Shell. Blah, 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 blah. Yeah. Oh, now. Yeah. Okay. Yeah. Yeah. Certain things like realizing that your galaxy is actually. Is it the accretion disk? I think the accretion disk we use specifically for things that are closer to it, but it does seem to be what is locking everything in place. And it does seem to usually be there with pretty much every large galaxy we've seen. Oh, we need to find the dark matter. Okay, and we'll get to that next because where is it? Let's bring up. Okay, we're gonna go to our friend Anton over here. Feel free to check out Anton's channel. He doesn't do as much social media anymore, but
Hello, wonderful person. This is Anton, and today we're going to discuss a somewhat intriguing mystery in regards to missing stars, or technically stars that vanished.
okay. So let's go back for a second. So what are we even talking about? Okay, well, let me go back to the other picture. Okay, so the whole thing that we're going on here is all right. In 2000, so we've been observing these different stars, and this was in 2007, and then approximately, I think like 3 or 4 years ago, started to change in its intensity and temperature, and people were like, "Oh, maybe it's getting ready to go supernova. We're gonna see something spectacular," and then oh, just kind of like vanishes. Now, upon further investigation, apparently there was about 3% of the mass of that star that was detected as like kind of a shell of a dust cloud going around it. And you're sitting there and you're like, wait a second. Did this star just directly collapse into a black hole? Or what we conceptually refer to as black holes, dark stars, or whatever you would have it. Um, Now, again, I had heard this. Casey had brought this up to me, and I've seen some other things where apparently you have a bunch of stars. We've observing these stars for years, and all of a sudden, it's start blanking out of existence. The general gist from the video, according to Anton from the paper, is that right now they're estimating maybe about 30% of stars this happens to. I'm like, really? So what you're saying is, if you have stars along a certain mass scale, some of them just kind of directly collapse into black holes. This seems to be a new version of interpretation of how we think things generally happen. Because at least when I was coming up within school and everything, it's like, all right, no, some star, it's just going to turn to a white dwarf, or there's a supernova, there's going to be a neutron star, maybe a black hole. We're not really sure. Sometimes it can be hard to figure out, but there's going to be a big explosion, big, massive force throughout the cosmos. Uh, well, because now again, I am not an astronomer nor cosmologist. I am a dude on the internet. I'm just saying that is it possible that we might have a little bias towards supernovas? What? Because we could see them. They are observables to us. Whereas the something just goes and just more or less direct collapse mostly. And again, there was a bit of a dust cloud and stuff over there. So maybe a small on stellar scale explosion. You probably wouldn't want to be hanging by the star when that's happening because who knows what's going on over there. But at least according to observations, it does seem that some of these stars may actually have a direct collapse. So that's something that people have been talking about. Oh, and also the apparently as our ability to detect things within our cosmos increases as our measurements are getting better, apparently we're finding a lot more black holes than we had originally thought. So and again, I'm just following the train of logic here. I'm like, all right, so number one, there's a lot of dark matter out there. We have no idea what's going on. If we also have some vanishing stars that don't seem to be leaving enormous supernovas and everything, is it possible that perhaps the dark matter we're looking for, very often in the form of like axions or WIMPs or whatever theoretical dark matter particle that we have yet to observe, could explain all the stuff going on? That's more of Occam's razor. And it's like, well, isn't the simplest explanation the easiest? Because what is the dark matter, so to speak, that we know? Well, black holes and neutrinos. Okay, so what if, because as we're searching for dark matter in these giant tanks of like xenon and noble gases, the problem we're running into searching for axions apparently is that those dang blasted neutrinos keep getting in the way. We're getting close to the magnitude. We're not going to be able to find the dark matter anymore. Why? Because it's going to be blocked by dark matter. It's not the dark matter we're looking for. It's those dang blasted neutrinos. I mean, what if, just hypothetically, the dark matter we're looking for is the dark matter we know? It just happens to be maybe a little, maybe a lot more than a little bit of it because the stars have been disappearing for a while. And we haven't factored that in that maybe a lot of these not non-ginormous stars. I think the star from that article is like a like seven-ish, 7.5 solar masses, something like that. Um, if the red collapse has been going on for a while, might that explain where all this matter's been going, readjust, and coincidentally, maybe the dark matter we're looking for is the dark matter we haven't been looking for. Basically, I don't know. Don't they say something about it's better to associate with the devil you know than the devil you don't know? Now, again, I'm not saying one should practice any type of religion or anything like that. Hey, you go your way, I'll go Yahweh. I'm just saying that wouldn't that explain a lot if what we're looking for? It's kind of like was the Professor Keating. A lot of folks still use it. It's like, all right, you get a person, and it's like a drunk person looking for their keys. And it's like, what are you doing? I'm looking for my keys. Did you lose them over here? No, but there's light over here. Why? Because there's light over here. Whereas, okay, if you're looking over here and you're not finding it, maybe you look over to where you kind of know, maybe the black holes and everything. Maybe even people have been saying for a long time, it's like, now cosmology isn't broken. Now I'm not trying to break cosmology, even though I host a show that's called Breaking the Multiverse. That's up to interpretation, may depend upon the observer. But all I'm saying is a lot of folks have been mentioning that perhaps early galactic formation didn't quite exactly happen as we have conjectured it would be, or how we had thought. So, what happens if There's a lot more dark matter in the form of black holes. If all of a sudden those masses kind of were out there and there were more stars at one point, wouldn't those stars be sending out a lot more neutrinos until they collapse into black holes? What the heck am I saying? The claim is, what if the dark matter that we're looking for is the dark matter we know, aka there's a lot more mass out there as black holes and neutrinos than we had previously thought. Doesn't doesn't that solve a lot of problems? And we don't need to introduce new things. Now, I'm sure this claim must be wrong. Why? It has to be wrong. Be- because if it wasn't wrong, then a lot of people looking for dark matter might lose their jobs. And here's the thing: we should have a balanced, a diverse approach to science. Why? Well, you don't want to put all your eggs in one basket. Why should anyone listen to just a crazy dude on the internet? And I am a crazy dude on the internet. But every once in a while, crazy people notice things too. That's one of the things that I've noticed. That's one of the reasons I'll have some different folks on. Hey, I might have Stephen Wolfram on. He's fairly established, but he's also kind of outside the grain and a lot of different folks as well. I've had Jonathan Garrod on, but before a lot of folks realize that a lot of the Wolfram Physics Project is kind of the garage search for hope via metamathematics or something. It's uh, you see interesting folks. They have interesting things to say, and heck, I even had was it Bill Manuel on the other day because number one, I talked to him on Discord. He seems to have noticed an interesting thing. Went through some calculations, did a quick search, didn't see any literature over a one over log four relationship to the mass energy equivalent of a black hole divided by into its number of requisite Planck areas. So for a one Planck mass black hole, you have a 16 pi equivalent, and then it ends up being you calculate the temperature, so it's temperature over 8 pi, and then you do the Hawking thing, and then you have an 8 pi factor, and then yada yada. It ends up being 1 over log 4. That was from the other day. Don't worry about all of that. Uh, but it's when somebody notices something interesting, and even Rick publicly has shared Archimedes' formulation for gravity, where it's like, well, do do we need to have the mass terms in the numerator, or could we look at it from the other way? And then all of a sudden, it's like, wait a second, 2 to the 7/12. That's, oh, that 1.4, was it 98, 1 point, something like that, ends up being the inverse of 6.7, yada, yada, yada. Oh, it seems to be the string of digits for gravity. That's a very interesting. I haven't heard anyone else bring that up. So these are things that I think are worth considering. And especially if the ideas haven't been explored before, once you start exploring a new idea, you never know what you could find. Now, again and again, a lot of this stuff, it's like, well, anybody could find that. I'm sure there are people have. And apparently, there's a thing within history that I think it happens all. Apparently, it allegedly has happened a lot within mathematics. It's you have some of like the most brilliant minds, and they come across something, and they're like, "Oh, that's trivial. Somebody must already," and they don't even write anything about it. They don't even, and you'll go through like their old journals, and it's like, wait a second, they found this. It took like another 20 or 40 years for someone else to notice the same relationship. That's why I think publishing things and getting things out there into the greater consciousness, if you would, of humanity is a good thing. It also doesn't hurt that the internet timestamps and dates everything. So it's one of those things where it's like, yeah, no, I'm writing a paper right now. I'm going to submit it to the Wolfram Complexity Journal, and then I'll swap it over to LaTeX because Wolfram prefers the Wolfram things, and Physical Review and those other journals, they prefer LaTeX. That's totally fine. I'll play the game. You'll put it in there. That would be direct to the point. I'll submit those things. But also, it's like, oh, this is a cool idea. Let me do a YouTube video or something on it. Because these YouTube videos, remember, are published on YouTube, brought to you by Google and ABC Corporation, I believe. Uh, pedantic poking aside, let me grab a quick swig of Sprite. Let's See what else is going on. See Kali talking about brown dwarfs. Let's catch up. As I drink my own hair. Pardon. I think it's something that's about 10 to the 5 times 10 to the negative, like 10 joules per cubic meter. I believe that's the approximate vacuum energy. It's something like 5 protons per cubic meter, or at least the energy equivalent thereof. Yeah. Oh, well, that's the other thing. So technically, I don't think they're supposed to be any brown or black dwarfs, so to speak. Um, Yet, if we're going by the standard 13.8 billion year cosmological lifespan now, I'm not saying that observers like us, we may not have come, I'm not saying we didn't come into existence as we know it around us 13.8 billion years ago. I'm personally a big fan of, yeah, maybe things are a lot bigger. Maybe we've been around a little bit longer than we think because if, I don't know, if JWST, if we're looking back, and we're supposed to be looking back like 500, like half a billion years after the Big Bang or whatever the heck happened. I don't know. I wasn't there. Uh, but if something like that is happening, it's like, well, we seem to see some fairly mature galaxies. Some of them seem to have carbon in them, but that's not supposed to happen until we've gone through our population. Oh God, how do they do it? Like the population three are the OG stars or something like that. And we have like a reverse scale than we should really be using. Um, but it's very interesting. So because if our realm of persistence, our colloquial universe, in quotations, was older than 13.8 billion years. Yes, I know. I'm very stunning and brave, willing to conjecture. I think T is greater than 14 billion years. I know. Maybe it's totally wrong, but it might explain a lot. I believe Professor Gupta out of the University of Toronto, he did this paper that caused the whole pizzazz after Joe Rogan like retweeted him, and it's like, oh look, oh yeah, we're gonna stick it to the astronomer, to the cosmologist. Oh, he's conjecturing it's like 26 billion. Well, I mean, that would have a lot more time for galaxies to form, do this, that, and the other thing. So doesn't mean it's right, but we're trying to model because we're inaccurate. We know we're wrong. We're trying to be less wrong so we could be more right. Isn't that how it goes? Less than, minus than, confidence levels, something like that. But I just find it very interesting that as we're learning more, it seems that things are simplifying, if you would. And let's actually go into, I think, direct collapse. Black hole. Okay. We'll go to our friend Wikipedia. Why? Because it's here. It's also the first thing that comes up for what I'm looking for. Okay. So, direct collapse black holes, DCBHs. Oh, yes, we have the best acronyms in all of the multiverse. Are hard mass black hole seeds that form direct collapse of a large amount of material. They putatively form within the redshift rate. Oh, okay. So this is mass black hole seeds. Okay, is this how we're getting Planck? Okay, this thing, unlike seeds from the forced population of stars. Okay, this population three are formed by a direct general relativistic instability. They're very massive with typical mass of which tens of five solar masses. This category of black hole seeds was originally really. I think that was only a 7 mass black hole. Seven. Let's go back to what Anton says. Wow, this article may need to be directly. Let's see. In 2016, a team led by Harvard University astrophysicist Fabio Pasucci identified the first two candidates for direct collapse black holes using the Hubble Space Telescope and Chandra X-ray Observatory. Two candidates with a redshift of Z greater than 6 were found in the Candelas-Goods S field. I have no idea what those things are. And mass and spectral properties predicted for this type of astrophysical sources. Particular sources were predicted to have significant excess Infrared radiation compared to other category sources of a high redshift. Additional observations, in particular with the James Webb Space Telescope, will be crucial in investigating the properties of these sources and confirm their nature. Okay. Difference from primordial and stellar collapse black holes. Primordial black holes are a result of the direct collapse of energy, ionized matter, or both during the inflationary or radiation surrounding an area, as well as direct collapse black hole as a result of collapse of unusual, dense, and large regions of gas. Okay. So I don't think they covered any of the things that we're actually talking about this article. This is actually fantastic because that actually means if there's something to this, we're literally rewriting the books, so to speak, or the Wikipedias. I don't know. Do people still do books? Yes, they still do books. Um, but let's see if there's any news. Okay. Here we go of of gentle black hole formation. Here we go. See, is there something that's not Eureka alert? Here we go. Let's do space.com. That sounds a little bit more, or perhaps less pizzazzy and everything. Okay. You gotta love it when something in the title says happy accident. Okay. Overall, it's not surprising that black holes should be in triples, but what's surprising is that the system held onto the outer star after forming the black hole. Oh, okay. First black hole triple system. Okay, blah blah blah. Black holes form during the violent death of massive stars and supernova explosion. But this surprising discovery could indicate a more gentle black hole birthing process called direct collapse. I don't think ever did I, in the history of my existence, would I ever utter the sentence, a more gentle black hole birthing process. We continue. As because of the origin of this black hole had been more violent, it would be supply a prenatal kick. Oh my God, they're continuing with the analogy that we're going to launch the loosely bound star out of the triple star system. Okay, the system in question is V404 Cygni. Yes, it's not an error, at least not yet. Located within the Milky Way and around 8,000 light years from Earth. The so-called X-ray binary of the black hole and its victim star were previously known. The system has been well studied. However, a deeper investigation performed by a team led by Kevin Burge from Massachusetts Institute of Technology, MIT, reveals that this binary actually sits at the heart of a triple star system. Okay. Yes, advertisements. Good old. You can tell. See, I just like to see a little pre-thing that tells you the percentage of the screen area that is covered in ads. And I feel like you should have a filter process. You can be like, all right, I'm not going to go to any place that's like it has more than 20% ad things because it's like nothing, nothing says scientific integrity like scrolling through and then seeing an ad for Best Buy. I mean, at least kind of like makes some sense, but I'm just saying. Oh God! Imagine if we had a ranking system that would like ruin. That I don't know. Would it ruin Google? I don't know. They might have more money than who knows. Okay. So ultimately, this is basically where is nature? Okay, let's see. Will you let me in, nature? Okay, I still need to log in. Okay. So there we go. Evidence suggests that when combat objects such as black holes and neutron stars form, oh my God, they actually used the natal kick during which the stem of the remnant gas gains momentum. Observational evidence for neutron star kicks is substantial. It is limited for black hole natal kicks. Some proposed black hole formation scenarios may result in very small kicks. So, all right. So what I'm taking is they're using natal kick for the birthing process of black holes to describe supernovae. Yes, I can see you. Welcome, Quant. Good to see you, my friend. But okay. So what if this? I'm going to stop using the birthing scenario. It makes me feel very uncomfortable. Maybe it's because I don't have a uterus or anything like that. But okay. So when black holes are made, this appears to be the claim. It appears that the claim is maybe there's a big, massive kablooey, some type of supernova or something like that. Or if it happens to be under the right conditions, it just literally go and maybe a small of the shell of a couple percentage of its mass coming out. But if 97% of that is actually going into the formation of the black hole, might that explain the missing stars? All these stars, they just seem to go missing. I don't know. Maybe a black they got eaten by a black hole. Maybe somebody put a Dyson sphere up around them and they're extracting all its energy. Or is the simpler solution maybe it just directly collapse into a black hole? It just goes into a black hole. And if there's a lot of black holes out there, because we haven't factored this into the equation in any substantial amount, might that be the missing dark matter? Again, this is terrible news, if true, if you're looking for other types of dark matter that we might not be able to observe because dang neutrinos will get in the way in another couple orders of magnitude. Those dang neutrinos get in the way that how are we going to be able to find the dark matter that we've conjectured but never be able to actually physically like observe? I'm just saying that if Occam's razor suggests the simplest solution is likely the correct solution, and now, and again, we're going to have to analyze and we're going to need other samples and other eh, things that we can observe to be like, all right, this appears to be a thing. But even now, if the current paper and the conjecture, what certain folks are claiming is true, it seems that maybe about a third, 30 percentage or so of stars just kind of go into black holes. Now, if that's been happening for a while, let's say in billions of years, that we've been having black holes, or at least rather than supernovas going kablooey, 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 a lot of it's just. And there's a lot more black holes out there, and we're discovering more black holes. Might the evidence suggest that the dark matter we're looking for is the dark matter that we already know exists? I know that makes many people very sad. Now, I'm sorry it might make you sad. It might be completely wrong. It might be completely wrong. Maybe tomorrow we're all like, we got the axion. It's right here. We got its mass. We have plenty of observations. We figured out what's going on. Now, if we don't, maybe this is just another path to consider. Maybe, I don't know. It's the black holes that are out there. If there's a lot of them, let's let's do this. Just continue onward. Okay, let's say that we have a space, variable circle. Okay, then we're used to our star, the bright little stars. Yes, starlight, star bright. Aren't you the tastiest star I see tonight? Yada yada yada. Okay, you got all these stars, but then rather than seeing all the normal stars that we would throughout there, we've got, I don't know, at least according to current estimates, figure about 13 billion-ish years for these stellar cycles to happen and everything. And then all of a sudden, well, these are the stars we see, but what if throughout there that's like, we got black holes and they just start collapsing, but we haven't figured that into our calculations yet. I'm just saying it might be something that I'm sure somebody's actually done this and modeled it, but you're going to need the experimental evidence. You're going to need the observations because you can conjecture whatever you want. I'm conjecturing all the time, but we need to go and follow the evidence. Not what we want it to be, and there are ways to do that. Maybe there's a 2 pi factor in there. Heck, I'm claiming there's an 8 pi factor in just because this thingy right here is probably actually right on the board because people pop in all the time and people are busy. They don't get a chance to always go and look for stuff all the time. So what did we do? We did blah 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 blah. Okay, so it was 8 pi times and it was blah, 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 Planck mass to the fifth divided by kilograms to the fourth. Okay. And that's what you get this value of right there. And again, it's we have zero significant digits of accuracy. So it's like, all right, if this is the magnitude, might this be an explanation? It's a calculation. Does it actually say what's going on? Lord if I knows. But I'm just thinking that, okay, we take what we know and we apply it as best we can, as simple as we can to the things that we do know. Is this an alternative explanation? Sure. Does it mean it's right? No. But that's science. It's the quest to be less wrong. All right. I know I've said that at least once more in this presentation, so that means we're in our final minutes here. Okay, we've been going for almost an hour now, but let's let's recap. So what if I should probably actually put that on the board. Let's go over here and we'll just wrap up in our little area over here. All right, so what happens if we do the little reverse of this? What if we do our kilograms to the fifth over the blank? Oh, no, we need to go. How did I do that again? We want to have the correct powers here. We want to be, there we go. Yeah, it's fifth over fourth. Okay. Kilograms to the fifth over the Planck mass to the fourth gives us basically approximately 4.457, 4.457 times. Uh, Terrible. Oh, God, I can't even write seven. Worst penmanship ever. It was my worst subject. Times 10 to the, is that 30? Yeah, 30 kilograms. That's right. 30 kilograms, which is approximately the mass of an A-type main sequence star. So 2.2 solar masses. There's a little symbol there. That's, yeah. Oh, no, we need M sub that. See, I'm slowly learning my notations. 2.241 big M with that little dot in the solar masses, which is approximately, again, mass A-type main sequence star. A-type main the sequence star. Cool. All right. And again, zero significant digits of accuracy, but it's just very interesting that something like that using a similar construction, basically just an inversion of what we done to help calculate the electron mass, as we went through a little bit earlier, um, it happens to just come out about the magnitude of about 1.2 stellar masses, or well, a little over 2 mass worths of the sun, just from just a simple thing like that. Now, is that telling us something? Maybe. I don't know. It's just a fun little thing to do, and eh, help me fill up an hour of time, Sean, with you all. So let's see. Do we have anything else? I think that's just about all. So yeah, we've gone over, yeah, basically just using the inversion of the neutrino thingy over there. I think if did we do an 8 pi? We might have done a Geesking thing. Let's do a quick Geesking. I think it gets us down to, rather than a blue type star, yellow type star, more like, I think it's about half of the sun's mass. Let's see. To figure not volume. Okay, all right. Boom, boom. Let's bring it up. Uh, Okay. So about 1.1 times 10 to the 30 kilogram. Okay, so about half a solar mass. Okay. So about one third the stellar mass scale, about half the mass of the sun. Okay. That's just an interesting little thing. And again, I'm not saying there's anything to this, but I just find it interesting that we get of the magnitude of basically the main sequence stars. That says I actually adjusted and don't block the things that I'm talking about because I'm a terrible presenter. All right, that expression gets us into the realm of basically at least the A-type main sequence of our stellar models that we have out there. And, well, if a lot of these different stars, depending on their masses and everything like that, um, if they are direct collapsing, more or less, and we're not seeing all the big cosmic kablooies that we were looking for, might some other interpretations come into play? Hey, Tommy. Yeah, we're just wrapping up. It's basically we might be angering a lot of people because basically, long story short, is the claim is apparently we've actually started to observe stars going from stars directly collapsing into black holes. So we might not need all the supernovas and cosmic kablooies that we've normally been looking for. If that is true, that means there's a lot of dark matter out there, so to speak, that we already know exists, aka black holes, because it's a lot more black holes out there than we had previously figured. That would probably explain a lot of what might be going on. And if there were more stars that we hadn't accounted for that went into black hole form, that means there would have been more stars initially. And when a star is out there doing its star things, it's also emitting a whole bunch of neutrinos. The other type of dark matter that apparently, according to our experiments within next few years, our search for axions and WIMPs, our search for dark matter that is theoretical will be blocked by the dark matter that we have observed via experimentation. So, yes, scientists search for dark matter obscured by dark matter. This is the dark matter you're looking for. Okay. I've done that like 3 times now in here, so I think I've won up my welcome. But yeah, basically, that's the gist of it. So we can continue to do this throughout the week. I am planning on driving back to the East Coast probably towards the end of this week, probably maybe Thursday, Friday ish, something like that. So we won't do a show on those days. Might put up a few shorts or something, but I'm gonna drive across country and see if I can't visit some of the fine folks that I've met on the internet and through some other varying means and everything. So until then, take care of yourselves, everybody. It's a wacky and wild world out there, but peace out, everybody.